Hello and welcome to ML with AP. Today is Sunday and I'm back with data science and machine learning related interview question. Let's see the first question. The first question is, what is KL divergence? Explain where it is used in machine learning field. So friends, let's try to see what is KL divergence. So KL divergence. First, let's try to understand what is KL. So KL is named after the scientist, which I think I got their spellings right, but it is named after Liebler. Now, what does it mean? What does it tell us? So the concept is very simple. Suppose you have two probability density, okay, and let's say the second density is this, okay. So this is a probability density 1 and second density is this 2, right? The KL divergence tries to put a number or tries to quantify that how much dissimilar or similar these two probability densities are. So this is my frequency, this is over here frequency, and this would be my whatever variable, x variable. How much 1 and 2, how dissimilar they are, okay, between 1 and 2, and why it is needed, why it is important, the similarity or dissimilarity. Because in most of the time in statistics and machine learning, what we try to do is we try to predict. We do not know the true distribution. We try to predict or mimic the distribution, right? This particular KL divergence will ultimately tell you that how similar our prediction is to what the original distribution is, right? So this is the way to mimic what the true distribution, which is relatively unknown in most of the cases, right? That's why it is important in statistics and machine learning. Let's try to see with an example, okay? And to make matters simpler, what we'll do is we'll capture binary distribution, okay, or in other word what we call it Bernoulli distribution. So this is also called, and it is again named after Bernoulli distribution. What is Bernoulli distribution? Where the outcomes are two, right? True, false, 0, 1, 0, yes, no. If these type of events are there, what we typically call in the classification setting as binary classification, it is Bernoulli distribution. So let's try to draw two distribution, okay? So my first distribution is, and these are, what should we take? We should take the coin toss. So let's say the first distribution is fair coin. So if I draw a histogram, how it will look? It will look like this. This is my head, this is my tail, and both of them will be around 0.5. This is, let's say, the probability, right, of getting a head or a tail in case of a fair coin. You agree? This will be my probability for head and tail. Let's say I have a not so fair coin. We'll call it bad coin or something. Let's say bad coin. I do not know what I should call it, but let's say bad coin. So in case of bad coin, how bad that coin is, it will depend, right? But for example's sake, let's say that it is a, let's call it biased coin, maybe biased, right? That's the right word, biased coin, okay? So in case of biased coin, let's say it is heavily biased towards my heads, right? So 90% of the time it predicts head. How much time it will predict tail? This should be 0.1. 10% of the time it should predict tail, right? So I have two distributions. Let's call it distribution. This is P, and this distribution is Q distribution, okay? So now what is KL divergence is trying to tell? It is going to quantify or mathematically arrive at a number that how similar or dissimilar P and Q are, okay? This is the crux of it, right? If we are able to define between, these are two probability density, right? Probability distributions which we have for Bernoulli distribution, okay? heads and tails. Now how similar or dissimilar they are, right? Now one thing is that scale divergence, there are some formulas which are associated with it, but before formula we'll try to see that how we intuitively understand this, right? So if suppose friends, if we have to ask you that what will be the distribution of these two, how similar or dissimilar they are, what you will do? So what we can do is we can do that, okay, for case of head, let's say my p of h, my probability of getting a head, right? Okay, probability of getting a head, and if I divide it by not this, the q1, the second one will be the q. Let me erase this. Okay, I will select this QH. This could be one of the way to define that how similar my H or head distribution is. In case of Bernoulli distribution, how similar is my head distribution? Since it is a probability, we are capturing probability, it makes sense to divide it. Okay, so if the number is very high, if the number is very like close to 1, what it will prove? That this and this are very similar, right? They are similar items. If it is very far away from 1, right? Then what it will tell you? It will tell you that they are very dissimilar. But how dissimilar? Then again, we'll see that what a numerator and denominator, both pH and QH are positive numbers greater than 0, then the range of H or this number can be between what? Ultimately it can be 0 maximum, or on the positive side it can be infinity if QH becomes very small, right? This is the range, right? This will be the range of this ratio, correct? So closer to 1 it gets, similar the probability, right? Similarly for our tail scenario, right? Tail scenario, what it will be? We can write that P tail by Q tail, right? This we can write, correct? The probability of getting tail for the P distribution and quality probability of getting tail for the Q distribution, and when we divide, then this is one way of measuring it, right? But the question is the measuring both head and tail for both the distribution, not individual class, right? So what we can do is that, okay, we have arrived at this. Let's say that we take a weighted average. Okay, so let's say this number is h. We'll take h plus t and we'll divide by 2. We'll try to do the weighted average where both h and t carries equal weight, right? So it will, or we'll take the mean of these two numbers, right? We'll take the mean of these two numbers, and they say that, okay, this will define as a numerical quantity. This becomes a numerical quantity which should represent that how similar or dissimilar. Makes sense? Probably these things make sense, right? Now let's try, there is some problem with that. Let's try to see what the problem is. Okay, so in case we do this, then what will happen if we try to arrive at a quantity like this? Then what will happen is that, what was the P? The probability of head was 0.5. So my PH is 0.5. My QH is 0.9, right? My P tail is 0.5. My Q tail was 0.1, correct? If I arrive at this, then it will say that, let's calculate the formula. 0.5 by 0.9 plus 0.5 by 0.1 divided by 2. That is equal to 5 by 9 plus 5 by 2. Do you see, friends, a problem over here? These two numbers, one number is far outweighing the other number, right? The first number is 5 by 9, which is like half. The second number is just 5. So this always happens in the case we are taking the ratio of two probabilities, right? So it will always happen, and this is when the case is 0.5 and 0.9. If you case a more skewed case, right, instead of 0.9, if it is 0.999, then this difference will increase further up, right? So there are two problems. The problem one is that we should not take there should be some scaling which we should do over here, right? Some sort of a scaling, right? Or a standardization, normalization, right? The second thing we should do is over here, this doesn't look like equally weighted. We shouldn't be doing equally weighted. Why? Because one is overshadowing the other, right? The one number is overshadowing the other. So what is the solution for that? Whenever we have to do a normalization or these type of things, then log comes to the mind. So the natural log is the natural thing, right? So let's see, what we'll try to do is, we'll try to put this log, okay? So let's put it, okay? So ln pt or ph by qh. This is my first ratio of h. Of t, again I will do a log normalization, right? So pt by qt. Let's see why this will help us, and probably we can see it with a spreadsheet which I have already created. So this is the fair coin, right? My probability is always 0.5. Not so fair coin, getting ahead is 0.9. Okay, so if this is the combination, right, fair and not fair is 0.5 and 0.9, then what is my h? H is ph by, what is my h? My h is ph by qh, right? pH is 0.55, pt is 0.5. This is the situation which we are dealing with, right? We are dealing with. And these were uneven numbers. This unevenness increases drastically. Let's say if it is 0.1 and my unfair coin or bad coin is 0.01, this becomes like this. This number is skewed further. And somehow if it is like 0.5 and the unfair coin is 0.999, like in 10,000 times only one time the tail will come, then can you see the h and t, how diverged they are, how dissimilar they are? That is the case. And if we are doing a log of that, a natural log of that, then if you notice, instead of ht, which were so diverse, if I did a log transformation, they become relatively on the similar scale, right? Everything is around between 10 to 0 or 10 to 2, right? No number is, so that's the beauty of the scaling, right? So these numbers, after we did a log normalization, after that these numbers come to the similar scale, right? Now let's see what we should do about the second problem. Was equally weighted was also not right. So scientists thought that if equally weighted is not, then what should be the weight? The weight should be proportional to what? Proportional to the probability of getting that event. So what KL divergence finally boils down to is, and it is, the formula is written. I was trying to give you the intuition, but the formula is written that the KL divergence of distribution P and distribution Q is equal to summation P of x, and I will tell you just in a minute what is x, px by qx, okay? And this x is nothing but your, like in case of Bernoulli, it will be two classes, right? Two classes, correct? The first class and the second, like negative or positive class. So the x is nothing but the number of classes which we have in case of our setting. So our setting is equal to 1b, I is equal to 1 to 2. Okay, now if we expand this particular thing, and this is for the discrete, right, Bernoulli distribution. So KL for this continuous variable would be, we have to do an integral of px ln px by qx into dx, right? So this will be a continuous. Okay, now this is what the KL divergence belongs to, right? And we intuitively arrived at why there is a log, why it is getting divided, and why it is multiplied by this, right? And we are kind of understood that what KL divergence is, right? So in case of binary problem, what it will be? In case of binary discrete problem, how our formula will look like? Our formula will look like P, and let's say I'm shortening this as P, okay? So P ln P by Q plus, what will be the formula? The tail will be 1 minus P, right? If P is my getting a head, the probability of getting a tail will be 1 minus p natural log 1 minus p. This is the second event, right? The tail event. This is the for the head event I am doing. This is for the tail event I am doing. 1 minus p by 1 minus q, right? I'm just shortening. I'm removing the x over there. So this is what? This is for the h, head. This is for the tail, right? This event. And this event, obviously, if it is in case of binary or Bernoulli, if it is p, it will come 1 minus p over here. P, similarly 1 minus p, q 1 minus p. I hope you are getting this. Okay. Now, friends, the question is that where it is used in machine learning. So one place definitely it is used mostly in information theory, neural networks. But one place where you definitely we have dealt it earlier in our videos is logistic regression. So logistic regression loss is log loss. In case of binary classification, it is called what it is called? Binary cross entropy, right? So KL divergence is nothing but a measure of measuring the entropy or the difference between two distributions. So binary cross entropy, this loss is usually measured in case of logistic regression, right? And what is the logistic loss? If you friends recall what is logistic loss, it is represented again as P yi ln P yi hat. Now let's see, I is equal to 1 to 2. In the case of what? In the case of our binary classification, it will expand this. But let's say, what is yi? This was my observed, right? This was my predicted, correct? So friends, can you relate that this observed and predicted? Observed was the initial distribution, let's say P distribution, and this Q distribution is the predicted one, right? This is the difference. Now let's see that how it is related to KL divergence. Now in case of two-class problem, what will happen? I'm just shortening it. Pyi ln Pyi hat, okay? And your this is our binary cross entropy, right? Binary cross entropy. Let's say in case of our this particular thing, right? In case of two-class problem, this was the thing. How this thing can be written down further, okay? Let me write it down. P ln P by Q plus 1 minus P ln 1 minus P by 1 minus Q, right? This is what it is written, right? Correct? Okay. So let's see how it is written down. Now, if we expand this thing, this will become P ln P minus P ln Q, right? How it will, this thing will expand. This thing will expand as ln 1 minus P minus ln 1 minus Q, okay? And with P minus P ln 1 minus P, and this P and over here, this will become P ln 1 minus Q, right? This is how it will expand, correct? Now let's try to rearrange this. I'm taking this term first, P ln Q, okay? And minus and if you rearrange this, then again it will come as 1 minus P ln 1 minus Q, right? Correct? And the next terms will be P ln P plus 1 minus P ln 1 minus P, right? This is, it will all break down into these. We can rewrite, we are just rewriting this into this form. When we rewrite, friends, we notice that this particular, the second terms, these whole terms is only dealing with P, the first distribution, right? KL is always in terms of one distribution given other distribution, right? And calculating the difference. This becomes sort of constant for this, right? So ultimately KL is nothing but your, and this, friends, if you notice this particular thing, this thing is nothing but your binary cross entropy loss, right? This thing is nothing but your binary cross entropy loss. Why? Your binary cross entropy loss was P ln Q, right? For I is equal to 1 to 2. If you expand this, this was nothing but P, ln Q, and in the opposite case, what will happen? It will happen 1 minus P ln 1 minus Q, right? The negative class case. So our binary cross entropy is nothing but our Kehl divergence, right? So this is where it is used in case of logistic regression. This is the way we can answer. Okay, so that was the first question. Let's move on to the second question. Okay, explain how to find correlation between a categorical variable and a continuous variable. Okay, so the question is that how do you find the difference between a categorical and a continuous variable? So let's see. So we already know what is a categorical variable, right? And a continuous variable. Continuous variables are numbers, numericals, right? Which extend from minus infinity to plus infinity. Okay. Categorical variables are discrete. These are discrete. So like yes, no, high, low, medium, or categories. Like if the fruits category is there, then apple, oranges, all those kinds. So that's why these are called categorical variable and continuous variable. Now, the question is that how do you find correlation between continuous and now between two continuous variables? To find the correlation is very easy, right? How do you find correlation? Correlation, what does correlation tell you? What does correlation means? Let's see with the example. Okay, so this is my scatter plot of a data. Okay, and what does it tell you? That if y goes up, my x is also going up. Correct? So the question was that correlation between a categorical and so my y is going up, x is also going up. If my y is going down, x is also going down. And correlation tells you about the strength and the direction. It tells you about the strength of the nature and the direction of the nature. So it is going up, going up, going down, going down. Similarly, if there is a thing like this, right, a distribution like this, then this would be the line. In this case, y goes up, x goes down. Y goes down, x goes up, right? So in case of numerical, it is very easy to find the correlation, right? Pearson correlation coefficient. But in case of numerical and categorical, how you will find, right? Because you need to know the number, right? Because to find the correlation or the Pearson's correlation coefficient, you need to have the numbers to play with, right? How you will find it otherwise. So there are certain techniques. The first technique is, the short answer for this is that you cannot have totally defined correlation between a numerical and a categorical or continuous or a categorical variable. What you can do is you can find the relationship. You cannot define the strength of those relationships like how you define between two numerical variables, but you can define the nature of the relationship between a categorical and a numerical variable. The first technique which is used is called z-test. There are various actually, z-test or t-test. Now how we can employ this z-test or t-test, right? Let's take for example, we have a data, okay? So the data is salary, and salary is like, I'm just putting some number, 5, 7, 10, 12, 13, 15, like. And we have also another information, let's say that this belongs to a female employee. This also becomes to female, this becomes to male, this becomes to male, and this becomes to female employee, right? So female employee has what? 5, 7, 15. And the data for male employees we have is 10, 12, 13. The question which may come to you is that, and to find the correlation, not really correlation, but the nature of association, is that question will come to you that, hey, is female salary significantly lower than male salary? Right? That kind of question will come, right? And how we can solve this through a z-test or a t-test? Through a z-test or a t-test, we know that what is the standard deviation, what is the distribution of this, right? for this particular category and this particular category. And then we can say that after that, that okay, the mu of this, the average of this, right, or the mu of this, are they very different from each other? Is their standard deviations are very different from each other? And then statistically using the Z or T test, we can say that okay, are they very different, or are they similar to each other, right? That is how the first way of doing it. The second more structured way of doing this, and which is usually practiced, is through ANOVA, and typically one way ANOVA. Okay, one way ANOVA. And why it is called one way, we'll just see. But what is ANOVA? ANOVA is nothing but analysis of variance, and this is especially designed for such things, right? So how this thing will done now with the same data, we'll see that how we can do this particular thing, right? So there are three concepts: SST, SSW, and SSB. Okay, so let's say if this data distribution is over here, and this is for the female and this is for the male. This is the female, I'm just making it up, this is the female mu, right, mu female, and this is the mu male, right, and this is the range. We have drawn a box plot over here, right, for the female and male. Okay, now the question is looking at this, that are they very similar, or are they comparable, is the question. How can we numerically, like, looking at this looks like, oh, there is a great difference over here and all, but how can we statistically answer this question, right? That is done through ANOVA. So what we do is, SSB is called your sum squared between means between this particular category and this particular category. What is the sum squared of between, right? What is the difference of the variables, right? How far spread that out? That is being managed by sum squared within this particular group. What is the variance? How spread out the data is within this? How spread out the data is, right? And the addition of these two terms is sum squared total. Okay. Now I'll not go into the detail. You can look up that how these things are calculated. Okay. It's pretty straightforward. But the way we calculate after this, once you calculate the SSB and SSW, what happens is you calculate something which is MSB. You essentially normalize that, and MSW. How you normalize? You divide it by the degree of freedoms. So the degree of freedom for SSB is your n-1. Degree for freedom of SSW is n-k. What is k? The k is the class, number of classes. Okay, so this is how it's done. Once you receive these two values, what you do is that you divide MSW by MSB, and what you get is the F statistic. F statistic is also known as the goodness of fit test. So this particular thing comes as a number. Now in statistics, we'll always quantifiably like we should put a number to the thing, right? We should be able to with a great certainty we should be able to measure that which is higher, which is lower, and all, right? So what is F statistic again? Once you got the F statistic, then you have to know a F distribution. You have to see the F distribution. Okay, and again over here we'll have all the hypothesis tests, right? My significance is 0.05 or 5% significance on the confidence interval. Why we are calling it one way ANOVA? Because ultimately we'll see that this particular region, let's say my alpha or significance is 0.05 or 5%, 0.05, right? This area. So whether my F statistic is lying in this area or not, right? If it is lying in this area, then we can prove that okay, there is a statistically significant difference between the salary of the female and male, right? If it is not lying in that vein, again with the hypothesis testing, if you know, then we'll fail to reject, right? Then we'll say that, oh, okay, if my F statistic is lying somewhere over here, we do not know, we do not have true evidence to either deny or accept the null hypothesis and all those things. But this is how the basis of ANOVA works. And in case of you have to do a correlation, You cannot do a correlation between a continuous and numerical, but what you can do is we can have these techniques, right? ANOVA technique or Z strategy and T strategy, and we can arrive at that, okay, some nature, we can establish some nature between a continuous and a categorical variable. Friends, I hope you understood this. Let's move on to the next question. Next question is differentiate between multi-label and multi-class classification. Let's see. So the question is multi-label and multi-class. So what is multi-label and multi-class? First, let's try to understand. Okay. So suppose I have my features. Okay. I have three features, x1, x2, x3, and I have to predict y over here. Okay, but let's say what is multi-class? So some weight or color or some features are given. Okay, and here what I need to do is need to predict whether it's a cat or not a cat. Not a cat. Let's say my y belongs to cat or not a cat. If these two only categories are present, then where it will belong? It will still belong to multi-class problem, but a special class of multi we only have binary class, two classes. Okay. Suppose instead of this, our y has to predict whether it's a cat, dog, horse, elephant, and few other animals also. In this particular case also, a cat and a dog are mutually exclusive, right? Something which can be a cat cannot become a dog, right? Cannot be a dog. In this case, this truly becomes a multi-class problem. Why it is a multi-class? Because the number of categories for my y variable or my label, it is multi-class. It is not one class or not two class like binary. It is multi-class. So there are cat, dog, horse, elephant, different things. But all these things are mutually exclusive. So at the time of prediction, I will only predict either it's a dog or a horse or an elephant or blah blah and all those things. What is multi-label? In case, let's say we have y1 and we have to predict y2 and we may have to predict y3 also. Okay, and the problem is not this. The problem is that, let's say you have to predict over here. So a movie actor is given, okay, and language is given, and let's say budget is given, something like that. Okay, some features of a movie is given, and you have to predict whether this y1 predicts whether it's a family movie or a sci-fi movie or something like that, right? My y2 level predicts whether the movie will be a hit or a flop. My y3 predicts that, let me write it down. My y1 predicts family versus let's say action. Okay, my y2 predicts it's a hit or a flop. My y3 predicts something like it's a, let's say, some other genre, right? It's a horror, or the genre is over there itself. Let's say what other could be the class of a movie. The movie could belong to I don't know, like, let's say some class over here. Let's say it's a horror, or it's a, maybe it's a period drama or something like something. Okay, in this particular case, these y1, y2, y3 are not mutually exclusive, right? A film can be a hit, can belong to a period drama, and can be a family movie, right? Then what will happen? All three will be, for that particular case, all three will be y, right? What are the classes of the individual labels? These are individual labels, y1, y2, y3, right? These are labels. Over here, it was only one label in case of multi-class. Now we have three labels, and each label has two categories, or so one label can have multi-class also. The classes need to be mutually exclusive. Labels doesn't need to be mutually exclusive. That is the difference between multi-class and multi-label. Now there are ways we have only dealt with, I think in our videos we have mostly dealt with multi-class problem or binary classification problem like logistic regression and all, right? If you have a multi-label problem, right? Now let's talk about multi-class first. So multi-class you can employ if you have a binary classification multi-class problem, you can do logistic regression. What you can do is if you have a multi-class, truly multi-class problem, more than two, then you can do SVM, naive Bayes, decision tree, random forest, all those things you can do, right? If you have multi-level problems, then there are separate algorithms because you do not have to predict one, but you have to predict multiple labels, right? Then neural network is something which comes to my mind, that which can easily predict multiple labels at the same time, right? So this is the difference between your multi-class and multi-level. Friends, I hope you are getting the gist of it. Okay, let's move on to the next problem. Explain the difference between covariance and correlation. What is covariance and correlation? Let's try to understand. So the question is, what is covariance and correlation, and are they different or are they same? What is the difference between them? So let's try to understand that what is covariance. Okay, so first thing is first, that both of them tells what it tells about. It tells about the variance or the spread of the data. If suppose I have given a set of data over here, and I have to calculate the covariance or correlation, it will ultimately, whatever number will come, metric will come, it will talk about the variance of this particular data, how spread out the data is. But there are the differences, right? Covariance will only tell you that whether it's positively, like the relation is positive or negative. Again, with that example, I can tell you, right? So if this is like x1 and x2, covariance will only tell you if the relation is positive between x2 and x1, the relation is positive or negative. It will not tell you how strongly these positive or negative. The strength of the relation is not told in covariance. While on the other hand, if you have a correlation, then correlation is more standardized form of telling this strength of the relation and the direction of the relation also. So correlation will tell you, the correlation coefficient will tell you what is the strength of relation, okay? And it will also tell you the direction of the relation, right? It is positively correlated, negatively correlated, and it is more standardized. So it varies from -1 to +1. -1 totally negatively correlated. x1 is going up, x2 is going down by the similar speed. 0, no relation. +1 is strongly positively correlated. x1 going up, x2 goes up at the same speed, right? When I say speed, I'm loosely saying speed. It's like the strength is defined, that it's totally 100% positively correlated, right? So our covariance, and I think you can see it in the formula itself. Like if I have to define covariance, then how covariance is defined? Let's say I have n observations, then it will be defined as x minus h bar, x minus h bar, and my other feature is, let's say, y, so y minus y bar, right? And I will divide this by n, right? This is my covariance. So covariance, what it is telling you? It is telling you that this is positive, this is negative, right? It is, one will be, if it is negative relation, then one will be positive, one will be negative, right? That is the way covariance is calculated. It will not tell you the strength. But in case of correlation, let's say, what is the formula? The formula becomes this particular thing, your covariance of xy divided by the standard deviation of x and y. Okay, so what we are doing, we are standardizing it. Here we didn't do a standardization. Suppose the covariance come as 135. What does it mean? How strong the relation is, we do not know, because it depends on the scale of x and y, right? If y is in kilometers, it will come some other number. Y is in meter, a small number, it will come some other number. But correlation, since we are dividing it by sigma x and sigma y, which is the standard deviation, we are normalizing this whole thing. And hence we are restricting it between -1 and +1. That is the essential difference between correlation and covariance. Friends, I hope you got the idea of all those 4 questions. And with that being said, probably I will close this video is getting longer. I will close it over here, and I will see you next Sunday again with the new set of questions. Till then, have a good day and bye.